Hello, my name is Danming. Have you ever seen this in your life?
A broken glass gets restored. A balloon inflates itself. Cookie crumbs gather into one piece.
I bet you have never seen them in real life. Neither have I. Seems that in nature, things only go in one direction, but they never happen the other way around. But why? The answer lies in the second law of thermodynamics, that the entropy of an isolated system never decreases. In high school textbooks, entropy is defined as the measure of disorder. My bedroom especially conforms to this law. Every time my mom scolds me for messing up the room, I respond to her like this: "Hey, Demi, clean up your room." Mom, according to the second law of thermodynamics, it's a natural desire of my room to get messy. Okay, it's a joke.
So what is entropy?
Here, I'd like to explain the concept of entropy with an experiment. I'll keep running into the water. Guess what will happen next? Of course, the red ink will eventually spread across the tank. This is a typical process of entropy increase. To explain entropy, we'll use a concept called phase space. A drop of red ink contains about 1,000 billion molecules, with 3 parameters to determine the position of one molecule. So we need about 3,000 billion parameters to describe merely one drop of red ink. Physicists came up with a crazy idea. They attempt to combine all these things into one coordinate system. This leads to a 3,000 billion dimensional space called the phase space.
What the heck is that?
In this way, a single point in this high-dimensional phase space would represent a possible state of the entire red ink. In the beginning, the red ink has a small volume of V0, so that the system moves within a phase space region with size V0 to the nth power. In the end, the red ink spreads across the water tank with a volume V1. The system moves within a phase space region with size V1 to the nth power. We define entropy as a logarithm of phase space size. The equal probability principle says that the system is equally likely to be at any point in the phase space. So the probability of the system being in a particular state is directly proportional to its phase space size. For the red ink, the probability of it spreading across the tank is 10 to the power of 10 to the power of 22 times larger than the probability of it gathering into one drop. Therefore, once the red ink spreads, it is unlikely to come back. This is why entropy always increases. It is so impossible for entropy to decrease. The second law says the entropy of an isolated system never decreases. It always becomes more chaotic and more mediocre. And man does so as well. If he defers to the natural desire of entropy increasing and dawdles every day, he will definitely become mediocre. Only when he breaks the isolated system, steps out of his comfort zone, and continually learns from the outside, can he avoid entropy from increasing.